Okay, this is 6.6 day 2, second day of learning about vectors. Again, don't forget you have a formula sheet right here, 6.6 formulas. We're going to be talking about more of these formulas down at the bottom of the page. Okay, now we talked about magnitude as being a measure of the length of the vector. And we talked about that being the horizontal distance from the origin squared plus the vertical distance squared square root. Basically just the distance formula. And then there's a new kind of vector. So yesterday we talked about component vectors, we talked about position vectors, and today we're going to be talking about a unit vector. So basically a position vector is a vector that starts at the origin. A component vector is any other kind of vector that's kind of out there in space. But then a unit vector is a vector of length 1. So if you try to find the length, it would be 1 unit long. Now, you can write unit vectors in pretty much the same way as the other kinds. You can write them in this form where the notation is with i's and j's. And there's 2 different ways to do it depending on where you want the radical. Anyway, find the unit vector in the same direction as 4i plus 3j. Well, first of all, we have to find the length. The length of this vector, v, is the same as the magnitude, so which is the square root of a squared plus b squared. So we would take the square root of 4 squared plus negative 3 squared, which is the square root of 16 plus 9, which is the square root of 25, or 5. Okay. Now the unit vector in the same direction as this one would be found by taking the vector and dividing it by its magnitude. So you would take the vector v, which is 4i minus 3j, and divide this by 5. Now we've talked about how you can separate this into 2 separate ones, 2 separate fractions instead of 1 large fraction. So that would be 4/5 I minus 3/5 j, and the letters can be either on the top or on the side. So that is a unit vector with the same length as the given vector. Now sometimes they want you to verify that the answer actually has a length of 1. So we simply take this vector and we find the length of it. So there's not really a name for it, so I'll just say the square root of the horizontal component squared plus the vertical component squared underneath the radical. So 4 squared is 16, 5 squared is 25, plus negative 3 squared is 9, 5 squared is 25. So that gives you, if you add them together, 25/25, which is just 1. So yes, indeed, this vector that we found is indeed a unit vector because its length is 1. Now, this is where it really gets complicated. We can write vectors in polar form. Wow! Okay, this is what a vector looks like when it's in polar form. So, writing them like this can be a little bit tricky. This example is just wanting to remind you what a bearing is. If it's north and then 20 degrees east, this is your trajectory right here. This is north 20 degrees east. That's just a quick reminder of how that works as a bearing. This would be 70 degrees from the x-axis, which is this distance here, which is your reference angle. Alright, so then finding this in polar form, you would simply say that you are exactly at 70 degrees up into the first quadrant, and your vector's magnitude is 30, because that's 30 miles per hour. A lot of times magnitude represents a force, and in this case it's the force of the wind blowing at 30 miles per hour. So we would use this formula right here, our vector in polar form, and we would take our theta angle, which is 70 degrees into the first quadrant, and the magnitude is the force of that wind, which is 30, and we could substitute that in, and we could easily write this in polar form. If we find the cosine and the sine of 70 degrees, multiplied each one of those by 30, you get that. So, example number 2. If a jet stream is blowing at 60 miles per hour, 60 miles per hour is our magnitude. Okay? And the direction will give us the angle of rotation that we need. Okay, south and then east 45 degrees. So if we go south, like here's the origin, we go south and then east 45 degrees, it puts us here. Okay, so if this is our origin, where we started, and we rotated all the way to here, that's in the fourth quadrant, right? And we're 45 degrees short of 360 degrees, so that would put us at a position of 315 degrees. So, using our formula, the vector equals the magnitude of the vector times the cosine of the angle times I plus the magnitude of the vector times the sine of the angle theta times j. So magnitude is 60, so 60 times the cosine of 315 degrees times I plus 60 times the sine of 315 degrees times j. So we substitute these numbers in. Let's see, the cosine is going to be square root of 2 over 2, because that's a 45-degree triangle that you can draw right here, reference angle 45 degrees. So this distance here would be the square root of 2 over 2. This vertical one would be negative root 2 over 2. So I'd have 60 times positive root 2 over 2 times I, plus 60 times negative root 2 over 2 times j. So this one would be 30 root 2 I plus negative 30 root 2 j. And the final one, this is kind of a long example. Basically, we want to combine these two forces. Two forces, F sub 1 and F sub 2, have a magnitude of 30 and 40 pounds respectively, acting on an object. So you got these two things kind of pushing on an object. One is twice as strong as the other. They're pushing at different angles. So basically what I want to figure out is what's the what are each of these two vectors, and then can I combine them somehow? So the first vector is north, the direction is north 10 degrees east, so that would be, here's north, 10 degrees east of that would be right there. So basically, we're pushing up into the first quadrant 80 degrees, right? Because 80 plus 10 is 90. So the first vector, F sub 1, is equal to the magnitude of F sub 1 times the cosine of angle theta, I, plus the magnitude of itself times the sine of the theta times j. So vector 1 says that up here that the magnitude is 30, so that would be 30 times the cosine of 80 degrees times I plus 30 times the sine of 80 degrees times j. So cosine of 80 times 30 gives you 5.2 roughly, and sine of 80 times 30 is 29.5. The second vector is going north 60 degrees east. So again, we're in the first quadrant. You went north and then you fell over this way 60 degrees towards the east. You would be 30 degrees. So you would get 60 times the cosine of 30 degrees times I, 60 is the magnitude in pounds, and then 60 times the sine of 30 degrees times j. So that would be 51.96 I plus 30j. So you have these two vectors. So these are both acting on this one object. So you want to figure out how they both work together. All you have to do is add them together. So down here, if I add f sub 2 plus f sub 1, I get, adding these two numbers, the two I numbers, I get 57.16 I. Adding the two j numbers, I get 59.5 j. So the last part is just finding the, this, oh, you can see